we need to write down the Taylor series again. If a function f has a Taylor series expansion about a, then, okay, f of x is equal to the sum n equals 0 to infinity, the nth derivative of f evaluated at a divided by n factorial times x minus a to the n. That's something you need to know, but in this particular case, we're about to talk about what's called Taylor's theorem. It's going to be a good idea to write the first billion terms out. We'll use a dot, dot, dot. So if we do that, what's the first term, you guys? If you have that summation formula memorized, you should be able to plug in n equals 0 to remember what the first term is going to look like. What's the first term? And remember, when you see f superscript 0, that's just f. That's the original function. So you plug in 0, what's the first term? F of a. There you go. What's the next term? Plug in 1 for x now. F, what does f superscript 1 mean? Prime, yeah. Or you could use 1 if you wanted to, with the understanding that it's not an exponent, it's a derivative, a first derivative. Evaluated at a times x minus a to the 1 power, or just x minus a. Okay, we're starting to develop the pattern, but not quite yet. We don't have it quite yet. What's the next term going to be? F double prime. You plug in 2 for n, right? So double prime, or you could use a superscript 2 of a divided by, I'll put in 2 factorial to establish kind of the pattern, or at least start to, x minus a to the 2. All right, and then what's the, I'm not going to write this one down because I've got to write something else down. I don't have enough room to write it all. The next one would be, I would just write f3, or you could write 3, but eventually you have to start using the superscript numbers and not the prime notation, right? So I would just write f3 evaluated a divided by 3 factorial, yeah, and then x minus a cubed. You write that down, and then you got it. You've got the pattern, right? Let's go to the nth. Let's do a plus dot 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 and go to the nth term, and then we'll go. We have to go even further because it's going from the sum's going to infinity. But I want to make a point here. Plus dot 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 plus. Okay, the nth term you can just get from the shorthand notation. The nth derivative evaluated at a divided by n factorial times x minus a to the n. Okay, what would the n plus first term look like? The very next term after the nth term, that's what we just wrote down, was the nth term. What would the n plus first term look like? You got it. So f superscript n plus 1, the n plus first derivative evaluated at a divided by n plus 1 factorial times x minus a to the n plus 1. And then let's go ahead and put in our plus dot 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 because it never stops. I don't normally write down this much, right? Normally just after the first 4 terms, when, maybe one more than this one, and then plus dot dot dot, I don't bother writing this stuff down, but there's a reason for it. There's a reason for it. Okay, so any arguments there? Now that we have that in our brain right now, or right in front of us, we can talk about Taylor's theorem, and it might actually make sense. Okay, Taylor's theorem. Suppose the number a lies in an interval I on which f of x has n plus 1 continuous derivatives. Then Rn of x, okay, remember what that was? Do you guys remember what that was? F of x minus the nth degree Taylor polynomial. That's what it is, right? Turns out that Taylor proved, I don't know if he's the first one to prove it, but it's called Taylor's theorem, so he must have done something with it, that's equal to, okay, here's what it looks like. It looks like this, the n plus first term, except you put in a c where that a is. That's how you can remember it. So it's the n plus first derivative evaluated, I'll tell you what c is in a second, evaluated at c divided by n plus 1 factorial times x minus a to the n plus 1. That's the remainder when you take the nth degree polynomial and subtract it from f of x, which is the sum to infinity, right? Assuming it exists. Oh, by the way, so what is c? Well, c is some number that lies between x and a. It's in an interval between x and a. Okay. So how the heck do you prove that? Let's not worry about that right now. Let's concentrate on understanding what the darn theorem says. That's more important than proving any theorem, is understanding what it says. We often don't take the time to do that. So what it's saying is, okay, go back up here. The remainder. What is the remainder? You can point at it. The remainder is everything after the nth term. So the remainder is everything, including the n plus first term, but also the plus dot dot dot. That's the remainder. That's the difference between f of x and the nth degree Taylor polynomial, because guess what? This is, up to the nth term, this is Tn of x. It's important you understand that to understand the theorem. And that's why we wrote it out longhand. Do you guys see that? Yeah, the Taylor polynomial of degree n is always contained in the series, the infinite series, right? You just write it out and then you can point at it. It's everything from here on down that way. Then the tail of the series, the remainder of the series, tail of the series, is everything that way. So it's very important that you include the plus dot 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 there, right? Okay, so it's saying, this Taylor's theorem is saying that this remainder is given by this. Just this single term. There's no plus dot 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 here. C is some number. It's not a, not normally. It lies between whatever x is and whatever a is. So think about the beauty of this, for lack of a better word. If you can come up with the n plus first term of the Taylor series, then Rn, just replace a with c, and you can remember this. It's kind of nice. That's why I show you this one. Some books will show you different versions of this. I show you this one because it's easy to remember. Okay, so where does this come from? Don't worry, I'm not going to try to prove it, except for n equals 0. I can prove this for n equals 0. So how do I do that? Proof. By the way, this is, as you'll see, it's going to be a silly proof. It's a proof for n equals 0. So, well, big deal. I'm not doing very much if I'm proving it for n equals 0. Okay, if n equals 0, R0 of x, in other words, plugging in 0 for n right there, you end up taking f of x minus, f of a. Because if you think about it, t0 of x, go back up here. It's just, this is t0, the first term. All right, degree 0 Taylor polynomial. Oh, it's the constant term. So keep that in sight. So proving it for n equals 0, Rn of x is just f of x minus f of a. And then, when you plug a 0 in there, you get the first derivative, 0 plus 1. So it's f prime of c times x minus just a, because you're plugging in 0 there. Does this look familiar to anybody? From Calculus 1.
Oh, wait, that's
Okay. What do we call it in Calc 1? You're close. MVT, the mean value theorem. Okay, in Calculus 1 you called XB, but doesn't really matter what you call that. And then my proof is going to consist of this statement, C Calc 1.